All right, so welcome everyone, and thank you all for joining. Project Team 1 are presenting our database to monitor water quality parameters in surface water such as lakes, reservoirs, and rivers. Our team combines the talents of Ari, Chen, Melissa, and Niraj. My name is Ben, and I'll introduce us to the current problem with water quality monitoring. Water quality parameters are measured by stakeholders, including government agencies, nonprofits, water body managers, and universities. Though collecting these measurements is often funded with public tax dollars, the data is usually not accessible through a centralized database, as data management is often done by individual specialists or organizations, and it's rarely aggregated. Online aggregated databases do exist, but they often have incomplete, sporadic, or non-existent data sets. As shown, some queries return no data at all, and other queries return a single data point from over 10 years ago. Therefore, there's a clear need for a central database that makes data available to the public, but also meets the needs of the capital stakeholders, who are the researchers and the water body managers.
Yes, so to that end, we've developed a database that is able to tackle these challenges with our two key stakeholder groups in mind. First being the researchers and the institutions themselves who are going to be collecting the data with their variety of instruments, and then the water body managers who are responsible for ensuring that their water bodies meet the government regulations. And then tying those to the various water quality metrics that we allow the database to collect, such as pH, water temperature, various chemicals in the water, etc. And here's some key facets of the database. First, we have enforced foreign keys throughout the database, ensuring efficient connection between all of the tables for our stakeholders. Additionally, a join table was created between researchers and instruments due to the many-to-many relationship between them. Researchers can have multiple instruments they're responsible for, and for larger groups or maybe more expensive instruments, they have multiple researchers tasked to them. Additionally, we allowed for username and storage and password encryption for a sort of hypothetical researcher login procedure that could hypothetically be used for some sort of login UI that could hook up to this database. And then additionally, for analytical purposes, we added a meets criteria calculated field that checks for each record that an instrument collects. It checks to see if that water body specific regulation, if the value collected by the instrument meets that threshold or not.
So our first report and view aim to look at the annual physical chemical parameters. So to do this, we first created a view that leveraged subqueries and group bys to aggregate the various physical chemical parameters for each of the water bodies, as well as a metric that measures how many of the water bodies in our database actually meet the criteria set by the regulation standards. The next report and visualization we looked at were the monthly averages of turbidity, total dissolved solids, and average pH. These were grouped by month and by year for each of the water bodies. And as you can see to the left, we've been able to create a visualization that shows the distributions and trends of the three parameters over time. This shows the versatility of our database, allowing researchers, institutions, and water body managers to track the physical properties of the water bodies over time and make adjustments as needed.
For other visualizations, we wanted to showcase how our database enables water body managers to track the health of bodies of water according to various metrics. So we started by using a histogram to track the distribution of pH levels across various states, and also a box and whiskers plot to track the distribution of water pH levels, not only across different states, but also different kinds of bodies of water. In conclusion, we designed a water quality parameter database that allows for aggregation and monitoring by researchers, public health officials, and water body managers. We implemented constraints and password encryption to ensure the integrity and data security. For the purposes of this database, we use both artificial and real data that provide a glimpse of how the database would be used and its potential. Looking towards the future and the next steps, we realize that there is a real need for such a database. However, this requires not only buy-in from data collectors and data analysts, but also uploading data from real-world instruments, stressing that stress check the integrity and the features of the database, but also that continuously collect data more often than once a month. Thank you so much.
That's it. Thank you, everyone. We're happy to take any questions you have at this time.
Hey, so this is Ron from Team 22. And I wanted to say I think you guys did a great job. Really good presentation and really great sort of storytelling there to explain the business case. I was wondering, it seemed like you were talking about disjointed data sources. How many data sources do you guys end up tapping in order to fill out your database? And what was your biggest challenge in getting the data from some API into the tables?
Yeah, that's a really good question. I can answer that. In the beginning, we just filled our data with artificial data just to kind of get a sense of how the relationships would work and test the integrity of our data checking. We had a hard time actually finding continuous data that we could feed into our database. A lot of times, and we kind of talked about this in the beginning of the presentation, a lot of times the data is gathered by a specific group or a specific person, and they kind of keep it in their private data. And if you go online to one of these central databases, they'll have like random data points that you can't really put together and create a good visualization. On one of the slides where we had the time series, that was captured from a single sensor. And so it was useful to get information over time, but it was at just a single location. And so this kind of addresses a real world problem that a database like this could address, and that if a lot of different researchers all have buy-in to a single database and agree to upload data to a central database, it's a lot easier to access it. Currently, how things are done is you have to go onto like a state website. So for example, Massachusetts, they have their agency that does water quality management, and they'll have individual CSV files that are for like a handful of places. And for one watershed, maybe they'll have like 5 data points or 10 data points. And another problem is a lot of these sensors measure different parameters. So you can look at pH in one location and you'll look at turbidity, which is like how cloudy the water is, in another location, but it's really hard to compare across geographic locations. So to find real world data, as much as we wanted to put a lot of real data into this, it was really hard to find it.
Yeah, I think we ended up with similar challenges and very different data sets. So I think that might be kind of a across the board or industry kind of thing. Thank you.
Yeah.
Yeah, and just speaking from industry experience, though, I was working in e-commerce rather than water environmentalism. But yeah, even then in the industry, this is a very common thing to have data sources coming from places with different formats, different columns, sometimes CSV, sometimes APIs. And that's one of the biggest challenges in the industry.